morning session. Today, I'm excited to introduce Nati Srebro from TBIC, who of course needs no introduction. And Nati is going to tell us about applying statistical learning theory to deep learning, what we understand, what we need to understand, what we need to understand, what we need to rethink. But I really like the title. That's what's on the x-axis. And as many of you in the room, like myself, we've all learned a lot from Nati over the years. So let's get to learn about.
Okay. Thanks. So I think that the schedule says, I think I'm going to talk about implicit bias. I've spoken about implicit bias quite a bit, actually also from this stage specifically. And I will talk also about implicit bias, but I think what I'm going to give is a bit more just following up on Spencer's tutorial from yesterday. So yesterday, Spencer gave us a very nice kind of introduction to what I would consider the classic view of statistical learning theory. And what we'll try to do now is kind of take what Spencer taught us yesterday and see how it applies or maybe doesn't apply to deep learning. And in particular, we will also talk about implicit bias, and we'll talk also quite a bit about benign overfitting that Spencer mentioned yesterday briefly. So I saw that there are going to be quite a few talks later on, both this afternoon and later on this week, about benign overfitting. And so I did want to spend some time, getting everybody up to speed in the tutorial, though I'm sure that I don't know if the people that are speaking about benign overfitting are happy or not happy that I'm either taking away their thunder or setting things up nicely. What you should think is I'm setting things nicely so you can hear about current work on that. Yeah, and as Priya mentioned, this talk also has kind of okay. So two things you should keep in mind to prime you for the tutorial. There are two things you should kind of keep in mind that we'll be continuing to think about. One is how much does deep learning what we see in deep learning, does it fit with our classic understanding and we can use our classic techniques, or is it that our classic analysis techniques, the classic view of statistical learning, like just breaks down and we need something completely different? So like how much can we use tools developed over the past like 5-6 decades or so? And I'll already spill the beans and tell you that for the most part, the answer is that we can. We didn't waste our time over the past 6 decades. The ideas and methods and techniques that developed are applicable. We just have to think of how to apply them correctly. And the second thing is this subtitle, and this is the question that whenever you want to ask a question, or even if you don't want to ask a question and you don't know what to ask, then this is the question to ask. Like, what's on the x-axis? Okay, so we'll be looking at this, and I think this is an important question to ask also when you look at a paper. You see papers and you see a plot that looks like this or like this or like this or like something else. And always you should ask, okay, what am I actually seeing here? What's on the x-axis? How should I interpret this? This x-axis, is it the correct x-axis or not? The y-axis will usually be something like error. Maybe that's easier, but the x-axis will be spending a lot of time thinking about whether it's the correct x-axis. Okay, so as I mentioned, we'll start by just very quickly recapping Spencer's talk from yesterday, just to remind us of the notation and get things set up to how we're going to continue talking about him. So we're going to be again redefining supervised learning, which Spencer already did, talking about the estimation error, the approximation error, measures of capacity or uniform convergence. And one thing that Spencer also mentioned, maybe the main thing I want to get out of this is this notion of inductive bias, that from my perspective, it's kind of the central notion in machine learning, and we'll maybe understand a bit better what at least I mean by inductive bias. We'll then look, as I mentioned, how this fits in with the deep learning, talk also about implicit bias. I mean, we did advertise it in the talk title, so I feel like we should talk about it, but it's also important, and we will definitely spend quite some time talking about it. And as I mentioned, also benign overfitting. Okay, so feel free, we have plenty of time, I think 2.5 hours together this morning. And so feel free to ask me questions whenever, if it Don't be afraid to ask questions about anything. Maybe I'll answer, maybe I won't answer, but you can always ask. I mean, if I don't answer, it might be because I don't know the answer or just because I rather not answer right now, but you're not going to know. Okay, let's start. So we're going to talking about the exact same setup that Spencer mentioned, which is supervised learning. Supervised learning, basically, we have some unknown joint distribution over instances or inputs X and labels Y, right? So you can think of it, an image and what's in the image, a character and what's in the character, whatever you want. We'll be most looking at Y being just binary, and what we want to look is what we want to get as a predictor, some mapping from X to Y that's good on the population and minimizes its expected loss. So this is really what we care about. But we don't know the joint distribution, so we don't actually know what the expected loss of any predictor is. We want to do it based on a sample drawn that will throughout assume is drawn IID from the population, and a DTE, which I think I don't see her here anymore, though I don't recognize anybody with the masks. Yesterday told us about how this assumption that we have samples drawn IID from the population we care about actually doesn't hold in practice, and it never actually holds in practice. But in this talk, we'll definitely, I think throughout the entire talk, stick to the assumption that we have actually samples drawn from the distribution. Right, so the central object of study is a learning rule, which is just a mapping from the training set to a predictor, okay? And so the question is, the first question is, if, is there a good learning rule? Is there a learning rule that always succeeds in finding a good predictor, okay? And the answer is no, right? So this is, and this is referred to as a no free lunch theorem, which says basically no learning rule is good, right? For any learning rule you give me, there exists some reality, some population for which this learning rule is horrible. Okay, so what does it mean? So of course, there could be realities for which there's no predictor that's good, right? Because if you have a reality where Y is just independent of X, and there's just no predictor that's good. Okay, so that's not interesting. But the thing is that there's a reality, population, a source distribution, right? I'm going to be using these three words interchangeably. For any learning rule, there is a reality for which Y is just a deterministic function of X. There exists a perfect predictor with zero loss, but your learning rule is not going to find it. Okay. Right. So more formally, when you say how bad it's going to be, not only is it not going to find it, but it's not going to be doing any better than chance. Okay, it's not going to have error much better than 50%, like for binary classification. So error 50% error, I can always get just by random guessing, and you're not going to do any better than that. Well, you can do maybe a bit better. So you can do a bit better by an edge, which is number of samples over the size of your domain, the number of possible instances. How can you do that? How can you get an edge of number of samples over number of possible instances? Yeah, so just memorizing, right? I mean, if you have only, if there are only 10,000 possible inputs, 10,000 possible images in the world, and you saw 1,000 of them, we already saw 10% of them, you're going to have an edge of 10%, okay? So that's not really learning, but what the no free lunch theorem tells us is you can't do any better than that. For any learning rule, there is a reality for which this learning rule is not going to do any better than memorizing, okay? And of course, with the size of the domain X, usually we think of it as either huge or really continuous, so infinite, and so you can do, memorizing is useless, and you can't do any better than chance. Okay, so this is bad news, and it says you can't learn. So how can we learn? Okay, so in order to learn, we said, so what we said here is that there's no learning rule that's good for all realities. For every learning rule, right, there's some reality for which it's bad, okay? And so in order to learn, what we have to say is, well, it's not that I don't really care about all realities. Okay? I don't think that all realities are really plausible, okay? So I have to limit myself or focus or bias myself onto certain realities, right? And that's what I refer to as an inductive bias, right? So the inductive bias, we can think of it as, so the inductive bias is the bias that tells us that biases towards some realities over others, right? It tells us that our learning rule is not going to work out for all realities, it's going to learn over others. And we can see this in two different ways, right? So we can either think of it as an assumption about reality that makes our learning rule that makes a learning goal work, right? So, okay, sorry. I'm a bit out of it this morning. Okay, so you can see it. Sorry, we can see it in two different ways. We can either see it as a bias that biases our algorithm. So we can see it either from an algorithm perspective or from an analysis perspective. So you can either say our learning rule, okay, is not going to, I can't hope to capture all realities, and so I'm going to bias myself towards certain realities. So in that sense, the inductive bias comes explicitly from the the inductive bias comes first, and then we design our learning rule biasing ourselves to certain realities. You can think of it as a kind of, roughly speaking, a prior. Okay, although I definitely don't want to think about it as a prior, right? So it's going to prefer a certain relationship between x and y and x, certain realities. Another way to think about inductive bias is in terms of the guarantees, right? So we said that you can't get guarantees for any you can get guarantees for any realities. So you can think of the inductive bias as what are the properties, how do you break the no free lunch? What are the properties of reality that you need in order to make your learning goal work, right? For example, that there exists some hypothesis of a certain form that explains reality well, then we can say our learning rule is going to work. Okay, so maybe to make it more concrete, the most simplest maybe type of inductive bias is kind of this flat inductive bias. And flat inductive bias just says that some realities are plausible and other realities are not plausible. One way we're going to even look at it, we're just even look at the relationship between y and x. So some relationships between y and x are plausible and some are not plausible. So we have this family of possible relationships between y and x, possible predictors h, and we're only focusing on them. And so if you think about it in terms of assumption, we say that there exists a predictor of this form that has small error. Okay. Okay, so we're only going to, and so I'm referring this to flat because inside this class of possible predictors, you can think of it maybe as linear predictors based on a certain set of features. We don't have any, we're kind of like, if you think of it in terms of a prior, we have a flat prior inside this, like all of these realities that are plausible are equally plausible, okay? And then, as we saw yesterday, the kind of correct learning rule to use is empirical risk minimization to minimize instead of the population risk, the empirical risk. And we can guarantee that this will be a good learning rule by getting a uniform convergence guarantee over all predictors in our class H. And what we can get then ensure is that if there exists a good predictor in our class, we're going to find a predictor that's almost as good. Almost by how much? It's exactly the Rademacher complexity. I think maybe the way that Spencer defined it, I'm missing a factor of 2 here, or maybe not. I don't remember how he defined it. Okay, it doesn't matter too much. And this Rademacher complexity usually scales as something like square root of the capacity of the class divided by number of samples. Okay, so what is this capacity of the class? So the easiest way to think about the capacity of the class for binary classification, the capacity of the class is exactly the VC dimensions. We know the Rademacher complexity scale is the square root of VC dimension over number of samples. And what is the VC dimension? Why am I calling this also capacity? The VC dimension is the largest number of points for which you can fit anything on those points. You can fit like even random labels, right? So that tells you kind of how many data points for this class, how many data points is it able to fit without any assumption, right? So this is kind of like what it tells you how much different predictors are in this class, enough to fit like m points. And this is what this says is really there's a kind of a dichotomy here that if you have less than VC dimension number of points, then our assumption or inductive bias doesn't tell us anything, right? Because on less than m points, then anything is possible. And so I don't have any assumption at all. And so clearly I'm not going to be able to learn with less than m points. But what happens is once I have more than m points, I can start learning, right? The number of data points I need to learn here is proportional to this capacity. So I can, if a VC dimension is 1,000, less than 1,000 points, I can learn. More than 1,000, I can start learning. There's a kind of a transition. Okay. And the VC dimension, or the capacity, is generally like the number of parameters. This is exact for linear predictors. And for many classes, also the number of the VC dimension is roughly the number of parameters. We saw it sort of, we'll mention it briefly. Spencer talked about yesterday also for neural networks. And there's also a very, very simple argument that the VC dimension, or the capacity, is basically always number of parameters. So the VC dimension is always bounded by the low cardinality, right? And I said it's kind of the size of the class, right? Because to shatter m points, to get all possible behaviors in m points, you need 2 to the m predictors. And if I have, if I can describe my predictor using 1,000 bits, then that means I can have only 2 to the 1,000 predictors. So the low cardinality is bounded by 1,000, right? So the low cardinality of the class is always bounded by the number of bits I need to describe a predictor in the class. Okay. So now if I have a predictor that can describe by 75 parameters, 100 parameters, okay, then how many bits do I need to describe it? Well, I need 100 parameters times, I don't know, how many bits do you guys use to describe a real number? 32, I don't know, 32, okay. So I need 32 times number of times 100, or in general, the number of bits I have is like 32 times the number of parameters, okay? And so the VC dimension is always bounded by the number of parameters times the number of bits you use per parameter, okay? So this is kind of a very simple argument. It always tells you without thinking at all, then the VC dimension is always bounded by the number of parameters. That also means that whenever somebody tells you that, if you, I'm sure that many of you have seen, all of you, I hope, okay, so actually let's check and see we're on the same page here. How many people have seen the VC dimension before Spencer's talk yesterday? Okay, good. Everybody, and this is the first time I see everybody. Nobody's even shy to not raise their hand. Okay, excellent. So you probably also saw examples when you're shown the VC dimension, examples of classes with a single parameter where the VC dimension is infinite, right? I mean, you've all seen this. Okay, whenever somebody shows you such an example, either a class with a single parameter with infinite dimension, VC dimension, or any type, somebody tells you, oh, here's a class with like, p parameters, but has VC dimension p squared. Okay, in fact, Spencer did that yesterday. Whenever somebody shows you that, they know they're cheating you. Okay, sorry. Okay, because that necessarily means that if the VC dimension is larger than the number of parameters, that necessarily means that in order to shatter that many points, you need to use really a lot of bits per parameter, right? If I have p parameters and I'm going to shatter p squared points, I necessarily am going to have to use p bits per parameter. So that means that all your arguments are really based on this like super, in this real arithmetic or something like that, and this like super precise parameters, and that's not really how things really work. Okay, and so yeah, so you said capacity is number of parameters, but it can also be I
have a confusion over there. So that for neural nets, that d parameters would be d neurons.
No, number of parameters. So if you have a neural net, okay, so I think Spencer also talked about it yesterday, right? So if you have what are the parameters for, so we'll talk about it explicitly in a bit, but what are the parameters for a deep network?
Yeah, weights.
The weights, right? So it's number of weights, not the number of, okay? Okay. Okay, but so number of the VC dimension is always bounded by parameters, but as Spencer pointed out, number of the capacity. Okay, so now we're maybe not talking exactly VC dimension, but the capacity can frequently be much less than number of parameters. Okay, so even in situations where an infinite number of parameters, where we're in non-parametric settings, we can still bound the capacity and use like other techniques for that, like by bounding the norm or magnitude or scale of things. Like in the simplest example, if we have linear predictors, even in an infinite dimension, right? So this is what we do all the time when we use support vector machines. Or kernel ridge regression, we're using linear predictors in infinite dimensions, but we still bound the capacity by bounding the norm of the predictors. We know how to bound the capacity instead of the number of parameters by the squared norm of the predictors, squared Euclidean norm. Okay, great. So what's the game here? So he said that the capacity controls kind of, you can think of it as controlling this estimation error term, or number of samples we need to learn. But then we have also this term, which is kind of, what is this LH star? It's the best error I can get with something in the class, right? So you can think of this as the approximation error, right? And this leads to the classic decomposition of errors, an approximation error and estimation error. And this is like the main game in machine learning. We want to find hypothesis classes or assumptions about reality, then on one hand, are rich enough and large enough to capture reality well, to have a small approximation error, right? So there is a predictor in the class with small error. On the other hand, to be small enough, they have small capacity, and this estimation error term is small, that I can actually learn them with a small number of samples. Okay, so then we can say that, like, for example, this model class is good, but this model class maybe is not good. Why is this model class not good, like based on this cartoon? The reality is very different. So, right, so note that both these classes, they have kind of the same size. If if you believe this, or like, of course, what I'm trying to convey in this cartoon is the size of the ellipse is kind of the capacity. Both of them have the same capacity, right? If you prove a generalization bound for both of them, they'll look the same, right? They have the same capacity. So it's not that one class is better than the other because you can prove better bound for it. The reason one class is better than the other is because it captures reality well. Okay. Of course, I can have another class that maybe that's worse because it's larger, right? So we have to balance both of these things. But this is an important thing because that means that no theorem you're going to prove is ever going to convince me that one hypothesis class or one learning rule is better than another learning rule. Because as we said, every learning rule has some reality in which it's horrible, right? Really convincing me that one learning rule is better than a different learning rule, you can only do by saying something about reality. You have to say, something about reality. You have to say that this actually captures reality better. And that's not a mathematical statement. That's a question about reality. Okay. You might break it up and say, okay, I believe that reality behaves in this way, and this learning rule works well for this thing I believe, right? But ultimately, you have to make a statement about reality. Okay, but this is for flat inductive bias. We usually actually don't have flat inductive bias because usually, even if we say that, for example, I believe that reality is captured well by a sparse linear predictor. Okay, so when I say that, what do I mean by that? I don't mean that reality is captured well by a predictor with sparsity 7, or predictor with sparsity 15, or predictor with sparsity 50. Okay, what I mean is that, well, I think that sparse linear predictors are more likely than less sparse. So the sparser you are, you're more likely. Okay, so really, what I'm defining here is some kind of complexity measure that measures kind of the assigns some. You can think of it as a complexity, a prior, although I don't want you to think about it as a distribution, some measure of simplicity or complexity, or how likely each different predictors are. Again, like, what are you going to be biased more towards? We're going to be biased towards things that are simpler, where this measure is smaller. Okay, and one argue is that usually when you talk about most of our inductive biases really are in terms of complexity measure and not in terms of this flat hypothesis class, right? So we talked about sparsity, or maybe if you in high school, when you fit, you get some points and you try to fit polynomial through them, then you kind of prefer the lower degree polynomial, but you didn't know in advance what the degree is, right? So you have a bias towards lower degree. So you think in this case the complexity is like the degree of the polynomial. Even if you're just using linear predictions, you don't actually know which features you're going to have. So maybe you have some kind of complexity that having less features or simpler features. And all these examples are discrete, right? So we think of this discrete complexity measure like sparsity or degree of polynomial. You can also talk about continuous complexity measures like the norm, right? So if you're using, we mentioned support vector machines before, then there we're using linear predictors over an infinite feature space. Our feature space is maybe fixed, right? We fix the kernel. But then we're saying, oh, we prefer low norm predictors. But what norm? We don't say in advance that we want predictors with norm 37.653, right? We just say that I would be more biased. I would prefer a predictor with norm 37.693 over a predictor with norm 56.4, right? So if I have, if I have to choose between those two predictors, right, I'm going to choose the smaller one, right? Okay. And so I intentionally want to emphasize here first the discrete ones, because somehow we frequently associate when we're talking about discrete control, like dimensionality or rank or something, we think of the fixed hypothesis class. When we think about continuous control, we think of it in terms of complexity measure, but these things are completely orthogonal, right? You can have continuous or discrete, and then have either a flat hypothesis class or this complexity measure. Okay, is this clear? Okay, so how do we learn if we have with inductive bias, it's given by a complexity measure? So now what we want to do is actually minimize two things, right? We still want to minimize the empirical error, but okay, there's a typo here. Can somebody spot the typo? I intentionally put the typo. Did somebody spot the typo? Okay, so what we minimize is not the, we can minimize, this is our population error, which we can minimize. There's a hat missing here. We're of course going to minimize the empirical error. Okay, so we want a predictor with that both has small empirical error, but we also want to bias ourselves to its simple predictors, right? So we want a predictor that both has small empirical error and small complexity, okay, or is simple. Okay, so what do I mean by that? I mean, there are two objectives here, and those objectives might be competing with each other, right? So this is, and they generally are competing because, you know, usually the simplest possible predictor is going to have, like, what if I look at, for example, degree? What's the simplest possible predictor? Sorry? Oh, even simpler than that. Constant, right? Degree zero polynomial, but that's probably going to have horrible error. I mean, that's going to have, that's going to be a pretty bad predictor. Okay. So the simplest possible predictors are, if I look at norm, right? What's the simplest possible predictor? If I think of it SVMs or kernel ridge regression, or in general, like low norm prediction, what's the simplest possible predictor if my complexity measure is the norm of a linear predictor? Zero, right? The zero predictor. Okay. The zero predictor is, is going to always have, null error, right? Definition, right? And I'm not going to get anywhere, right? And so I always kind of have a tension between them. And so the way to think about this is a bicriterial optimization problem, right? So I have these two competing objectives, and here I actually did write it correctly: the empirical error on one hand, and the complexity on the other hand. And what I want to find is a predictor that's like as close as possible to here, right? That has small empirical error and small complexity. Okay, but that's generally not possible. Okay, so I have to compromise. So the way to think about this plot is like any possible predictor. I plotted the dot here for its combination of empirical error and complexity. And this yellow, or whatever color this is, are the possible attainable values. Okay, so the thing is that I'm definitely not going to want this predictor. Why will I not want this predictor? There's some predictor that, this predictor and predictor that has, this empirical error and this complexity. Why would I not want this predictor? Yeah, so I can do better. I can, for example, with the same complexity, I can get smaller error, right? Or with the same, or if I know, why do I not want this predictor, right? Because I can get either small error, or with the same error, I can find a simpler predictor that has the same error, right? So I'm definitely not going to want anyone on the, inside here. The only predictors I might want to consider are predictors over here. Okay, what's this? So this is, I think of it as the Pareto frontier. Is the predictors that are kind of, I cannot, any predictor here. This predictor, maybe I'm going to want it because I can't find a simpler predictor that has better error, right? If I want something with, I can find something with maybe smaller error, but then it's going to be more complex. So now it depends how I balance complexity and error. Okay, and what is this path? So this is the Pareto frontier, or the way we think about it in machine learning is usually the regularization path, right? So what's the regularization path? So one way to think about balancing the empirical error and the complexity is by minimizing some kind of linear combination of them. And again, I'm really apologize for missing either a hat or an S here. I mean, these are all empirical errors. Okay. This is particularly embarrassing because I already used these slides quite a bit, and probably the next time I'm going to use them, I'm going to forget to correct it. If somebody can remind me afterward and send me email to correct it, I'd appreciate it. And so we minimize some linear combination, and as we vary lambda, right, that's the trade-off between the empirical error and the complexity, right? So when lambda is very, very high, I really want something with small complexity, okay? And so even the expense of getting very high errors, I'm going to be somewhere over here. And as a lower lambda, I'm saying, okay, I'm willing to compromise in complexity in order to get something with smaller error until lambda goes to 0 and I'm over here, okay? But I don't really care about lambda. Usually when I go into this, I don't have some lambda in the same way that I don't know I want a predictor with norm 36.7. I also don't know that I want to use lambda 0.0734. Okay, so really lambda for me is just some nuisance. Really what I care about is this object, which is the Pareto frontier, the regularization path. And lambda, this formulation with lambda is just some way of exploring and getting all the predictors in this path. I can do it and also in other ways. For example, I can minimize the error subject to a constraint in the complexity, or minimize the complexity subject to constraint in the error, or do any other monotone combinations of them and vary the balance. The point is that I get essentially what I get is the set of all these predictors, and the way we actually select between these predictors is not by coming up with some lambda, but by using some kind of validation technique. Question?
Yeah, I guess I'm curious, like how we justify like the complexity measure as an inductive bias. Like, why would we want like, the simplest possible predictor?
Okay, so the way I think about it is the other way around. You have to have an inductive bias. You're going to have some inductive bias. I'm going to call your inductive bias the complexity measure. So the fact that I use the word complexity, I think somebody yesterday, I think it was Matush, who's still here. Okay, so Matush yesterday said that he doesn't know what simple means, right? Okay, I don't know what simple means either. Okay, simple can mean a bunch of different things. So this complexity measure is not some universal definition. There's no, in fact, I don't think there's a universal definition of what simple means and what complex means. Okay. Well, actually, maybe there is, but that's a different question. In a theoretical sense, maybe, and a syntactic theoretical sense, but there's no universal definition of what simple means and complex means. Okay? But rather, in order to do learning, you have to decide what simple means and what complex means. Okay? Because we said that in order to do learning, you have to have inductive bias. You cannot do learning without inductive bias. And that means that you're going to bias towards some things over other things. And I'm going to call the things you're going to bias to simple, just the name I'm going to call them, and the things you're going to bias away from complex. Okay? So if you're going to use, if your predictor is going to be, if your learning rule is going to be minimizing the norm of the predictor, I'm going to say that you're going to use a complexity measure, which is the norm. Okay, say which one, like the Euclidean norm, right? Okay. If your predictor is going to be trying to get the sparse solution, I'm going to call your complexity measure. I'm going to say that sparse is your complexity measure. Okay. Does that make sense?
Yeah.
So
I guess I'm curious, like what would be an inductive bias, a complexity measure that doesn't look like because these, I feel like you could squint at all these things and be like, well, degree of the polynomial.
Well, yeah, okay. So the thing is that it's not surprising because generally we believe that simpler things, we use. Okay, so it goes back to what does the word simple mean, and I agree with Matush. I don't know what simple means, right? But we kind of have this feeling, and this is formulated by Occam's right. We should always prefer simpler things. What does simpler mean? I don't know. Okay, so we have many different ways of saying what simpler mean, but it's not surprising that whatever we feel is a good inductive bias, we associate it with being simple. I'd argue that actually the way it works the other way around. That in your brain, when the reason you see all these things is simple is because you think of a good inductive bias as okay, it's simple. Okay, but I don't know. I can come up with a whole list of other things here. Like for example, I can write expressions, or you can write expressions that look very scary to you, or look scary to me at least. All kinds of that define all kinds of properties of functions that in some sense mean that they're simple in some way. I know, but maybe because they're not familiar to you, they're not going to immediately jump out as simple to you. Okay? These things I intentionally put here things that are going to be. The reason I put here these examples is because I think they're the simplest examples of simplicity. Right? But yeah, I mean, this is it really boils down to what we said before: is what is a good inductive bias? What makes something a good inductive bias? And I think something is a good inductive bias if really it corresponds reality. It corresponds well to reality. Okay. I mean, I'm going around in circles because I think as Matush said yesterday, I don't think there's an answer to this question.
That's good. Thanks.
Okay. Okay. So. Right. Okay. And then, so I'm going to refer to this rule as structural risk minimization. Why structural risk minimization? So this is a term that Vapnik introduced because, in some sense, instead of just minimizing the empirical risk, we're minimizing both the empirical risk, the approximation error, which is the empirical risk, and in some sense, the estimation error, which is the population risk. And how can we analyze this? So roughly speaking, we can now guarantee, and we can have a similar guarantee, and the guarantee involves also. It said that if there exists a predictor H star that's both simple, according to this measure, so low complexity, and has small error, I can compete with this predictor. And what's my estimation error term going to be? So it's going to involve the capacity of the sublevel set of the complexity measure, including it, right? So what's going on here? So the thing is that a lot of our study of statistical learning theory, like what Spencer mentioned yesterday, appears to be about flat inductive bias, right? We talk about uniform convergence of a fixed class. Is it really because we use flat inductive bias? No, we're not going to use flat inductive bias. But the thing is that when we use non-flat inductive bias, when we use a complexity measure, we can also think of this complexity measure equivalently as defining this hierarchy of hypothesis classes. What is this hierarchy? It's just the sublevel sets of the complexity measure, right? So each set here, I just drew 3 of them, but there's a continuous, if the complexity measure is continuous, there's a continuum of them, are just the sublevel sets of our complexity measure, okay? And then in order to say, how well we're going to learn or how well we're going to compete with some predictor H star, we have to find the sublevel set of, why did I, okay. Maybe I'll draw it here, okay. If there exists a predictor that we think is simple, like has small complexity and small error, then to say how well we're going to compete with it, we're going to have to find the sublevel set of the complexity measure that includes it, right? So it might look like this. This is this sublevel set, right? So these are, other sublevel sets of the complexity measure, right? We find the sublevel set that includes it, and now we have to ask, what is the capacity of this sublevel set? Okay, and that's the term that's here, right? And that's going to determine how many samples we need in order to compete with this predictor. Okay. So the learning theory, all our results for single hypothesis classes for flat inductive bias we can apply them also when we have this hierarchy of hypothesis classes or a complexity measure. Now, 2 things here I want to point out, and this is the terminology at least I'm using here. I mean, maybe other people use slightly different terminology. I distinguish between complexity measure and capacity. Okay, so the complexity measure is an arbitrary measure. It doesn't have to be, it's just what you think captures reality. Let me say we had, degree, sparsity, norm. You can come up with any norm as a valid complexity measure. In fact, any function, the complexity measure is any function from the predictors to 0 to the reals, positive reals. It doesn't really matter, okay? Because if I think the complexity measure, so the thing is that the actual numeric value of the complexity measure is completely irrelevant. What really matters is only how it orders different predictors, how it says that one predictor is simpler than another. So any monotone transformation is fine. So if I think that I'm going to use the complexity measure, which is the Euclidean norm, and Pragya is actually going to use the squared Euclidean norm, doesn't matter. We're using the same complexity measure, right? They're just different by some amount. The reason that we're using the same complexity measure is that we're going to have the exact same hierarchy of sets. Okay, so the complexity measure can be anything, and the numerical value of the complexity measure is completely meaningless, right? So if somebody comes up with, and this is something new, if somebody comes up with some norm that they say is a very good measure, and then they measure and say, look, I measured, in reality is well captured by a predictor with norm 536.7. What does that tell you? It tells you absolutely nothing, right? If they just divided that norm as the norm divided by 7, you'll get a different number, but it's exactly the same method, exactly the same learning goal. The capacity is a meaningful quantity. Okay, the capacity tells you really what is the size of a sublevel set in this hierarchy, right? How many random examples can it fit? Okay, so if you think of some, and know that you can think of this function, which is the capacity of a sublevel set at a certain level. Okay, that's a way of taking, so if, of putting meaning into a complexity measure. So come first, so say Sam came up with some norm and said this norm is great, and then he measured this neural net where he says this really captures because this neural net has a norm of 536.7, doesn't tell me anything. But now, if I actually know how to calculate the capacity of the sublevels, the capacity of the sublevel sets of his norm, and I calculate that, and I found that the capacity is 15,000, that number 15,000 is meaningful because I know that in order to learn that reality, to learn a predictor that's as good as that predictor that he has that has whatever norm I said, I need more than 15,000, maybe a bit more than 15,000 examples. Okay, that number now becomes meaningful. Okay, so also in particular, this is where our work in learning theory comes in calculating capacity. The complexity measure anybody can come up with. Okay, and you don't need, also know that for the learning rule, you don't need to actually be able to calculate this generalization, the capacity measure, which is generalization bound, right? That you only need to calculate the generalization bound, not in order to actually use the complexity measure, but only to understand it. Okay, so now that means that okay, but let's go back to here. So you said that before, oh wow, I'm going slow. Okay, let me try to speed up a bit. So we said before that our game was coming up with complexity, with hypothesis classes that capture reality well or not too big. But now really our game is, I'm going to come up with the hypothesis classes. We're going to come up with hierarchy for hypothesis classes or complexity measures, right? So we have these two complexity measures, each one represented by a hierarchy. And now I can say that one of them is better than the other. Which one is better? Which one is better, the blue one or the black one? The black one, right? Because the black one is going to capture reality with a smaller class, right? The blue one eventually is going to capture reality, but with a much larger class, right? Can come up with something like this and then say, okay, is this one better or worse? So again, I mean, depends on how close it is going to get to reality and how big is it going to be when it gets to reality. Okay, good. So this is, so far we didn't talk about deep learning. This is just classic learning theory. Now let's see how it applies to deep learning. So what is deep learning? I mean, deep learning is just learning using a particular hypothesis class, a particular family of hypothesis classes, particular inductive bias, which is that reality can be captured by feed-forward neural network. Okay, or at least in this talk we'll focus about feed-forward neural networks. I mean, we heard, did we hear talks? No, we didn't. But I think we'll hear talks about models that go beyond feed-forward neural networks. Right, and feed-forward neural networks are okay. So what do we mean that there's a hypothesis class? We have to think about it as a hypothesis class. So there's, the way we usually think about it is we fix the architecture. So we fix the graph, okay, and the activation function. And then we learn the weights, right? So the hypothesis class here are all the functions we use the inductive biases. I have an architecture. I'm saying a function represented using this architecture with some setting of the weights. Okay, so just a bit of the historical perspective. Now we associate feed-forward networks we associate feed-forward networks very strongly with learning, right? So if somebody tells you that they work on neural nets, you kind of assume that they actually work on machine learning. This was actually not the historical development. Okay, so anybody know when this model of a feed-forward neural net was developed? 90s, the 80s, the 50s. I hear 50s. Anybody better? Okay, so actually in the 40s, in 43. Okay, so it was developed by 1943 by McCollum and Pitts. So I really like the story. So Walter Pitts, he was a middle school dropout. Okay, so he grew up in a rough neighborhood in Detroit. His family would give him a hard time because he would go to the library and read books, and it was completely unacceptable. He actually, at some point, he read Russell's Principia Mathematica, and he had some comments about it. So he wrote Russell in Berkeley, in Cambridge. Russell was definitely not in Berkeley. He wrote Russell with comments about, this is when he was, I think, 12 or something like that. He wrote Russell with comments about Principia Mathematica, and as a response, Russell invited him to come to Cambridge and study there. He never actually made it to Cambridge, but when Russell was visiting the University of Chicago, so Chicago was a bit closer to Detroit, and he ran away from home at age 12? No, at age 15, he ran away from home to meet Stuart Russell in the University of Chicago. And he stayed in the University of Chicago. So then he just hung around the University of Chicago. He never enrolled. He just kind of hung around there, slept in the corridors. He was homeless, went to classes, occasionally popped into people's offices with clever comments. And then when he was 17 and still kind of wandering the halls of University of Chicago, then Warren McCullough, who was a more respectable person, he was a professor of psychology and medicine, actually not in Chicago, but in UIC, University of Illinois in Chicago, which was where the medical school was at the time. And he kind of found him and adopted him. He came to live with him. And they worked together, and McCollum was interested in neuroscience, and he got Pitts also interested in that. And they were really interested in the brain and how could the brain do stuff, like how could the brain compute, okay, what we call now compute. And they wanted to come up with a model that is, maybe inspired by their brain, but they're definitely not trying, they were fully aware that they're not actually doing neuroscience, that they're doing computation. They're thinking of, in general, about how can we compute? That was the question that they asked. So this is the early 40s. Shannon and Turing have just very recently, in the past like 3-4 years, published their work. Turing on with both of them. So this is Shannon's master thesis and Turing's paper about universal computation. Both of them basically asking, how can we compute, right? And suggesting people at the time were asking about, how can we model this phenomena of computation? Okay, so Turing modeled it with this Turing machine, and Shannon, which is probably the most influential, by far the most influential of these three, modeled computation using logical gates, right? So this was Shannon's master thesis. This now we take it for granted that if you want to compute something, you can use Boolean algebra representing, since we can build, once you construct logical gates, you can compute anything using Boolean algebra, right? And so Shannon had this model of computation using logical gates, Turing using the Turing machine, and they thought of, can we have a simpler model for computation? And their model for computation was the feed-forward neural net, exactly as we're presenting it here. The only maybe slight difference is we are talking about a general activation, and they looked specifically just at threshold activations. Okay, so but other than that, nothing changed since 1943 in terms of the model. This is feed-forward neural networks, as you can see them now in any textbook or any course, is exactly the McCollum and Pitts model. But their interest was not in learning, it was in computation. They said that, look, using this model, if we connect things in a particular way and set the weights in a particular way, we can compute any function. So the result, similar, mirroring Shannon's result with logical gates. They said you can do that also with these threshold units, which are more maybe simpler and plausible. And they were not at all talking about learning the weights. Okay, so that came up much later. As late as the 1950s, then neural nets were still studied as a model of computation. So Marvin Minsky, who is not a fan of learning at all, right? So Marvin Minsky really did not believe, right? He's not with us anymore, in learning, but rather in like kind of hard-coded AI. Marvin Minsky's, I'm not sure if it's actually his PhD thesis, but it's work he did while he was in Princeton. He actually implemented the McCollum-Pitts neuron, right? So electronically implemented. So their work was completely theoretical. Actually implemented it and built it with a point of showing actually how he built a computer using a neural net that can compute things. He had like about I think order of 50 to 100 of these neurons. You can still see some pictures of them, and to actually show you can build a computer using this. And you remember, at the time, we're still trying to figure out how to compute. Like the computers we have now, the von Neumann architecture was still kind of, it already existed, but only started to exist at the time, the early 50s. By the late 50s, Minsky lost interest in neural networks because he realized that von Neumann architectures are much more powerful than neural networks as computers, and so there's no point in neural networks. And so that was kind of maybe the end of neural networks as a method of computing. And of course, later on, we realized them as a method for, we're now using them for learning, right? And the main difference here is whether we hardcode the weights or whether we learn the weights based on data, okay? Okay, so with that said about, I think it's an important, well, other than the fact that I like this historical story about Pitts and McCollum, then I think it's important to keep in mind that the neural nets, that are now so strongly associated with learning, right? And learning is not, they were not initially developed for learning. Anyway, if we think of it in terms of learning, then we have this hypothesis class. We said that the hypothesis class, this inductive bias or hypothesis class, which is, all the functions are represented by a fixed architecture with different weights, And we know that the questions we have to ask about it are these two questions, what's the capacity of this class? This is going to tell us the sample complexity, and what's the expressive power? How well can it capture approximate reality? And yesterday, Spencer talked to us about the capacity of neural networks with a bunch of results, and then maybe the simplest result is if I have a neural network with some number of edges and certain depth, then I can with at least with real activations, the capacity is number of parameters times the depth. This is with real activations. If I actually have threshold activations, then this depth dependence goes away. And as we said, also, if you limit the number of bits per weight, then also this, for very simple reasons, the depth dependence goes away, and we can understand the capacity just in terms of the number of parameters. Okay, so this is at least one way of bounding capacity. And so have good answers, and these are results that started, actually the most recent are from the past few years, but started already appearing in the 90s. And now the second thing we have to talk about is the expressive power. How well can neural networks capture reality? Maybe this is the more interesting question. So what can we express with neural networks? So a bunch of stuff. So first of all, if we think about a general computation, well, we can express AND gates, right? So if you have a unit with a high threshold, then for it to be active, kind of you have you need all the inputs to be active. So you can express an AND gate, you can express an OR gate, right? If you have a unit with a low threshold. And interestingly, and this was maybe one of the interesting things about neural networks, unlike linear predictors that can express AND gates and OR gates, neural networks, we know, for example, can also express parities or XOR gates. And we also talked about it. Somebody talked about it yesterday, right? There was a talk about it yesterday, right? Matush, I think, right? And I think we'll hear some more talks about learning parities. And maybe this morning is there's something difficult to express with the linear networks. We can definitely express it with the neural nets. And the thing is that once we can express AND gates and OR gates, and we can also express negation just by having negative weights, then we can actually express any function. Okay, how can you express any function? Well, in particular, where we can express any function, we can build a circuit. Okay, so let's talk a bit about learning circuits versus neural nets. So we talked about the hypothesis class of neural nets. You can also talk about the hypothesis class of circuits. Okay, so what's the hypothesis class of circuits? It's a hypothesis class defined by actually two complexity measures: the depth of the circuit and the size of the circuit. Okay, the number of gates and the longest path from input to output. And it's all the functions, let's talk just about binary inputs and binary output, all the functions that can be implemented by a circuit with AND, OR, and NOT gates, with the size many gates and longest path from input to output size depth. Okay, so this is a valid hypothesis class. And again, thanks to Shannon's master thesis, we know that we can implement any function with a large enough circuit. But how do we relate learning circuits to learning neural nets, right? So know that when we learn a neural net, we say the architecture is fixed and we learn the weights. And here, when we talk about learning circuits, there's no weights. And what we're learning is the architecture. We're learning the interconnect between the gates. Okay? But still, I claim that if I can learn neural nets, I can also learn circuits. Or in other words, I can embed this class of circuits of certain depth and certain size in the class of in the hypothesis class of neural networks with a fixed architecture. How can I do that? Right, so how can I need to choose a single architecture for my class of neural nets is characterized by architecture, right? So I have to choose a single architecture, and with that architecture, I claim that just by setting different weights, I can implement any circuit. How can I do that? Yeah.
Do you have an architecture that includes all the different possible circuit embeddings and then have weights connected to them that are 1 or 0 depending on which one?
Right. So what I'll do is what
Daniel.
What Daniel suggested. So I have an architecture. What is this architecture? Includes all possible connections. I have a name for that architecture. A fully connected architecture. So I'm going to say I have a fully connected architecture, and now I'm going to choose which each neuron is going to end up corresponding to a gate, and the way I'm going to choose what's going to be connected to that gate is I'm going to choose which weights going into it are going to be 1, and the rest are going to be 0. And I also maybe choose which gate it's going to be by setting the activation, or maybe add NOT gates by negating, right? So so I can set the architecture by setting the weights, right? What we're doing here is basically, it's like programming an FPGA, right? So you're familiar with the FPGA, field programmable gate arrays. They're exactly that. It's a chip that includes, you get to choose your circuit. How do you get to choose your circuit? You have a fully connected kind of circuit, and you choose which wires to actually include and which wires to, which wires to bring in and which not to bring in, and also get to set the gates. Okay, good. So that means that this hypothesis class of neural networks is as powerful as hypothesis class of circuits, which means it can represent any function. So that's great. That has great expressive power. This is for this was for binary inputs, like plus minus one inputs. But we can get also similar results that tell us we can capture anything, or at least approximate anything, also for continuous inputs. So there's a whole bunch of results in approximation theory, these universal representation results that tell us that any function or any any function can be approximately by a neural network. Okay? So now, to make this concrete, I have to tell you exactly what I mean by any, like any continuous, any smooth, any something, any continuous, even any measurable function, and what I mean by approximated. But roughly speaking, again, I can capture any function using a neural net. So what's the problem with these results? So I have here results that tells us both for discrete and continuous functions, any function can be captured by a neural net. So that's great because it's, it seems that neural nets have amazing expressive power. We said we have to worry about two things, right? The capacity and expressive power, and expressive power is anything. I can capture anything. So what's wrong with these results? What? Right. So the thing is, like, it's true that I can capture anything, but using huge networks, right? So it's true that any function can be approximated by this circuit, but this circuit is going to be huge, which is going to correspond to a network that's going to be huge. Okay. How large? I mean, the size of the circuit is going to be, something like, where its number of parameters is going to be even more than 2 to the d. So d times 2 to the d if I have d inputs. Okay. And similarly for the universal approximation results, we have a size that explodes exponentially with the dimensionality. Okay. And this, of course, defies the point, because what we wanted is to be able to have a hypothesis class that can capture reality well using small capacity. And here it's huge capacity. It's exponential capacity. It's completely useless. We might as well at this point, if we need more than 2 to the d samples, we might as well memorize. We only have a domain of size 2 to the d. So really, the more interesting question is, what can small neural networks represent? Okay. So now we can think of what can it represent, and we can think about, first of all, kind of the geometric things, like, we can have one layer single hidden layer network can represent intersections of half spaces. And if we have like another layer, we can have unions of intersections of half spaces, and you can kind of play with this on and on. But really, maybe the most interesting thing to say is that neural networks can really represent, we can have this hierarchy where successive layers represent more and more and more complex features, right? In the same way they kind of have in this diagram, we have, we progressively build more and more complex things. And this is maybe if you go to actually, are there, I know, I mean, probably most of you, are there any vision researchers here? People working in computer vision? Anyone willing to admit it? Nobody? Okay, so I'm sure there are, you just are too shy. So if you go to a computer vision researcher, especially, but also others, and ask them, why are neural networks good? And say, they'll answer really about this expressive power, right? And they'll say neural networks are good because they can really capture this visual phenomena, or many phenomena well, because it says this hierarchy. And then the lower levels, I have this very simple features, like these low-level features, maybe edges. And then using them, I can then construct an intermediate units, represent some kind of intermediate, maybe geometric features. And then higher up, I have these higher level, almost semantic features, like, a bird or a wheel or a sun, or I don't know what I have here, right? And using these things, I can really, that means that they really, can capture reality does have this hierarchical structure. And so they can capture reality well. Okay, so maybe this is the most convincing reason to say that reality really can be captured well by small neural nets. Good. So this is maybe the view that we had so far, at least from the first half of Spencer's talk, Spencer's tutorial, that we can say neural networks are great because we understand their capacity. Okay, the capacity just corresponds, can be bounded by the size of the network, and using fairly small networks, we can actually capture reality very well. So that's great. Okay. But in fact, what I would say, I'm not a vision researcher, okay? I have a much better reason to say that neural networks have very good expressive power. So I said that neural networks can capture anything, but using huge networks. But I claim that even using small networks, I can capture anything. And why is that? So the thing is that any function computable in time t can be represented by a neural net of size t polylog t. Okay, so size almost size linear in the time. And I claim that really the only thing I care about are functions that can be computed efficiently. So this is not learned efficiently, this is computed efficiently. So to understand that, I want to take a step back and going to, what is machine learning? So my view of machine learning, machine learning is an engineering paradigm. It's an engineering paradigm of being lazy. Okay, so there are people here that are, maybe not lazy and are really good programmers. Okay, so if there's somebody who's and that's not the machine learning approach. The non-machine learning approach is to sit down and write a program that does something, right? So you want to do an OCR system. You know exactly how the letters, character recognition, you know exactly how all the letters of the alphabet, Latin alphabet look like. All of you do. You can all go and all of you know how to program, I hope. You can all go and sit down and program a character recognition system, right? So find, check if it has, two diagonal lines within a certain angle and a horizontal line between them, and call that an A. And if it's, so forth, right? You can all do that. But I wouldn't envy you, right? That would be a lot of work, right? The machine learning approach is to say, don't work so hard, just collect a bunch of examples of A's, a bunch of examples of B's, a bunch of examples in C, crank it up into your machine learning system and pop out the predictor, okay? But the thing is that since my goal is just to compete with with programming, eliminate the programming, then if the programmer can do it, then I don't need to, there's no point in doing it. Also, I'm going to learn something, and then I want to be able to get a predictor, and then I want to put your predictor in your phone, right? So the predictor better actually be implementable and be able to work reasonably fast, right? And so, so the only thing I want to care about is programs that actually run reasonably, in reasonable amount of time, right? And so in some sense, this hypothesis class, the class of all predictors that are efficient, is the only thing I care about. I don't care about learning some, if there's a reality for which there's no efficient predictor, I just don't care about learning it at all. Okay, so this, in my perspective, is the class of all functions. All functions are actually computable efficiently. Okay? And the thing is that if we said before, and what we saw is that neural networks can actually learn this class. So note that when we started by saying there's no free lunch, right? So that there's no learning rule that can learn anything. But now I'm telling you that there is a learning rule that can learn anything, right? Neural nets can learn anything because this is anything, right? In some sense. So what's going on here? So really we have to maybe think again about this no free lunch theorem. And it turns out that there is a free lunch, not this week, but and here there is here you're on your own for lunch. Sorry, how the Simons works. But you get free breakfast. But there is a free lunch because actually this class of functions can computed in time t can actually be learned with a really fairly reasonable number of samples. Only number of samples that corresponds to the runtime. And in order to see this much more directly, let's even look at a more generous class. Rather than programs that run in time t, let's look at the class of all the functions for which there's a program of length t. Okay, so that's any program that you can bound the runtime for program by its length. I mean, at least my model, I always like read the load the program to start with. So the runtime is always bounded by the length of the program is always bounded by runtime. So this is a much bigger class. In this class, clearly I can learn in time t because again, if I just look at the cardinality of the class, we said that or number of bits, we said that the capacity of the class is bounded by the number of bits needed to represent it. And if a program is of length t, that means it can be presented by t times, 8, 7, Unicode, 16, let's stick with 7, okay, by 7t bits, okay? And so that means that its capacity is only 7t, or order of t. Okay, so we can see that we can easily learn it with number of samples. It's only as long as the length of the program, which is really not much if you think about it. That means that if you have if there exists some predictor with 4 million characters, that's a pretty generous program. A program with a 4 megabyte program, then you can learn that with only a few million examples. I mean, that's really nothing in the scale we have now, right? So this is a really strong result. So what's the problem of this? Why don't we actually use these inductive biases? Why don't, and this is this bias of short programs or fast programs is absolutely the best inductive bias to learn. Like it can beat, if you can actually learn the program, do structure discrimination for error and runtime of the program, that's going to beat, I assure you, that's going to beat anything you have, okay, any other learning rule. So why don't we use this? What's the problem with this? Why don't we actually learn by finding a short program with small error, or a program with small runtime and small error? Anybody actually tried this? You want to try it now? Why not?
To optimize.
Yeah, so solving this ERM problem or structure minimization problem is very difficult, right? So optimizing over the space of all programs is very hard, okay? It's in fact, not only is it very hard, it's impossible, right? So finding the shortest, optimizing over all short, finding the shortest program that has small error is actually, it's actually not even computable. Or even finding, what's the best program with a certain length of small error is not computable. Because the program, like just checking if it has error, if it has small error enough, is not computable. So this is not only hard, it's like just outright impossible. Okay, we can make it we can make it computable, but at least if we stick to, instead of short programs, we stick to really what we care about, which is small runtime, and we are a bit careful with how we define things, then we can actually make it computable. But then it's not too difficult to show that ERM for programs that run in time t. So if I ask, what's the smallest error you can get with a program that runs in time at most t? Okay, this is a well-defined problem. It is computable. It's NP complete. Okay, so is that good news or bad news? Telling you that it's NP complete. Who thinks it's bad news? Only one. You guys are really not afraid. Who thinks it's good news? Why is it good news? Sam.
I'd be out of a job if it wasn't.
No, that's not necessarily true. Why is something being complete good news? Okay. So the thing is that if for all we know, it might be that p equals to np. I'm still holding up hope. And if p equals to np, then that means that we have universality, right? We can learn the class of all functions we care about. Okay. Now, this, again, this is like maybe the biggest and most important consequence of p equals to np. Okay. But that also means that if we want to get any negative result about learning, we have to, make some. We're going to have to make some assumption, like at least that p is not equal to np, and there is obviously important assumptions. Okay. Unfortunately, most of you, many of you actually, thought that it's bad news that it's NP complete, and that's kind of true because if p is not equal to NP, then that means we likely can't do solve the error. And you can say, well, okay, maybe p equals to np just tells me that ERM is not tractable, that it can't actually, there's no if p is not equal to np, there's no polytime algorithm that finds that does ERM over the class of program of functions computable in time t. But okay, ERM is only one way of learning. Maybe I can learn using a different way. Maybe, for example, if I train my neural net, that's not exactly ERM over short programs. Maybe that would actually solve the problem. Okay, so maybe somebody can come up with the, maybe Matush was really very smart, seriously, and maybe you can come up with a learning rule that does actually successfully learn the class of all short programs. So it means that Matush came to me and said, Nati, I have a learning rule, and I can guarantee to you that this learning rule, whenever there's a short program that gets small error, my learning rule will also output a predictor. It's not necessarily going to do ERM over short programs. It's also going to output a predictor that has error almost as good as not short, let's say short program and short runtime, right? So whenever there's a program with small runtime that gets small error, my learning rule is going to output a predictor that also has small error almost as good as this fast program. Okay, so should I believe Matush or not? I know the fact that p is not equal to np doesn't mean that Matush can do that, right? Because maybe of course he wants this to be efficient, right? Because maybe he has some other clever method of doing it. But the thing is that at least if cryptography exists, so we have to make, at least when one-way functions exist, we have to make slightly stronger complexity assumptions. At least if I believe one-way functions exist, and I do believe one-way functions exist, unfortunately, then I know that Matush is wrong, right? So whenever you see, and that's why Matush would never tell me that, right? But that means that whenever somebody comes to you and say, I have this thing and it always, works, right? Then you know that, something is wrong here, okay? So, and it's pretty easy to see this. So in some sense, if we could have such a thing, we could actually invert any function, right? Because we could get samples from that function, invert it, or another way to say it, one-way functions is the basis of cryptography, right? So cryptography rests on the fact that there's things that are easy to encrypt, but hard to decrypt, right? That's at least public cryptography, or also like general cryptography. You don't want, you want that even if you have examples of plain text and ciphertext, you don't want to be able to learn the mapping from ciphertext to plain text, right? And if you could do if you could have universal learning, you could break any crypto system. So in some sense, you either have cryptography or you have machine learning, right? It's either us or them. And unfortunately, for us, I think it's them. But okay, okay. So what's going on here? So in some sense, there's okay, let's see how this talk is going to go, because I'm currently where I thought it'll be after 15 minutes. I hope you're at least enjoying this. So what we said is, in some sense, there is a free lunch, right? So there's no free lunch, and I can't learn anything, but I can actually learn anything I care about. But this is, of course, a cheating free lunch, because I can learn anything I care about, but using a method that's not implementable. Okay, so really what I should ask is, what can I learn using a tractable method? And the real no free lunch maybe says is this, a complexity theoretic result. It says that at least if crypto exists, then there's no efficient method that can learn any efficiently computable function. Okay, and so now maybe we have to revise a bit what we mean by inductive bias, because just saying that we have an inductive bias and reality is captured well by a small capacity class is not really enough, because in particular we said that the class of efficiently computable functions is actually very small. Really, our inductive bias has to break two barriers, both this statistical no free lunch and the computational no free lunch, right? So if you talk about inductive biases, what is the bias that allows me to break the free lunch? I really need to talk about breaking both of these free lunches. And so really, when you have a learning rule, this learning rule, in order to work, it cannot work on any reality. It has to learn under some assumptions. And these should be both assumptions that are strong enough to break also this computational barrier, right? So now when we talk about inductive bias, it's important to keep both of these in mind. Okay, good. So let's go back to feed-forward networks. And we said feed-forward networks are in some sense universal, but the problem is, of course, computation. Now we're getting back to the second half of Spencer's talk, that it's much harder to actually, implementing ERM is very difficult. Okay, so what I mean in difficult, so Spencer showed in some very limited cases, right, where we do have some further inductive bias, we can maybe do ERM, but in general, it's it's a non-convex optimization problem. I mean, there's no difficult, but also maybe a better way to say it is just non-convex. We can solve maybe non-convex problems. But maybe more significant is to say that we just don't have any method that actually works. Like we don't know of any method that actually trains a neural network. Can we actually prove that no method exists? Well, okay, if you want to do ERM, then yes, it's very easy. So this is a result actually from Avram Blum's PhD, that even for a tiny network, even for the simplest possible network, non-trivial network you can think about with only 2 hidden units, then you can prove that if P is not equal to NP, there's no polytime algorithm that actually solves ERM on that problem. Not only solves ERM, but even just decides whether you can get a zero error predictor or not. So that means that even basically for any network architecture, proving that you can always do ERM is futile, right? If P is not equal to NP, you cannot always do ERM. But then we're back to this question of, okay, maybe Matush has a clever way of learning that's not with ERM, that does something else. Like, for example, one thing you can suggest, which many people suggest, is maybe if reality is captured well by a small network and I train a larger network, then it'll work, right? So now know that this goes beyond ERM, because now I'm not saying that I can necessarily do ERM on this big network. I'm saying that in order for that I can learn using a big network based on a stronger assumption that reality is explained well by a small network. But unfortunately, we know that even this is impossible. Okay? So we have very strong negative results that tell us that just the fact that reality is captured by even a very small, simple network, and we do have to go a bit above 2 hidden units. I mean, the latest and greatest, depends on exactly on which complexity or cryptographic assumptions you make, but you have to have a super constant number of hidden units. So even if reality is exactly captured by a network with some, say, logarithmically many hidden units, I know that there is no algorithm, no matter what that algorithm does, even if it tries to take in a much larger network, it does whatever it does, there's no algorithm that can always output a predictor that has error, better than chance. It has non-trivial error. Okay, so that means that just the assumption that reality is captured by a small network is not enough to break this computational bias. Note that in some sense, I mean, we have to work hard. We as a community, I had nothing to do with these results. We have to work hard to get results that are for even very, very small networks. But in some sense, to just say that there's no algorithm that can always learn just based on the fact that reality is captured by a reasonably small neural network, that we already right off the bat know that that's not possible. And that's really because of this generic approximation result, right? So in some sense, when somebody tells you, you have neural network and say, oh, that's great, this neural network architecture can represent anything, okay? That's what we're saying here, can represent anything we'd want, anything computable efficiently. It sounds like a positive result, but really it's a negative result. Because we already know that this inductive bias is not enough to break the computational barrier. And so if the network can represent all of this, that necessarily means that being able to represent, being representable this neural network is not enough to learn. So we already know that we cannot learn anything representable by neural networks. Okay, we have to work a bit harder to show that we can learn anything representable, even when neural networks are a single hidden layer and a super constant number of units. Okay, so where does this where does this leave us? Okay, so what we saw is that neural networks in some sense are amazing, can learn anything. The only problem is we can't actually try. I'll finish in a few minutes. Okay, so where does this put us? Really, that puts us, in the same place as using short programs, right? So short programs also are universal. They can capture anything you want, right? And they have small capacity. If I can actually learn, they'd be excellent learners. In fact, I promise you that learning using ERM over short programs or SRM with program length and length is going to be like the best thing you're going to beat any learning rule. Unfortunately, it's hard. It's provably difficult. And the situation with neural networks is exactly the same, right? They're universal. You can learn anything if you could implement ERM, but unfortunately, we provably know, subject to pretty reasonable complexity assumption, that's not possible. Okay, so both of these seem the same. But still, like, how many people here have successfully trained something with a neural net? Everybody, but okay. How many people have successfully trained something using ERM or SRM on short programs? Nobody. Okay. So why is that? I mean, it seems they're equivalent. Okay. And the real thing is that they're not really equivalent because short programs are really hard to optimize in practice. I can't even do local search in short programs, right? I mean, it's like okay, so short programs actually are incomputable, but even if I go to bounded time or something, I can't even do local search, right? So it doesn't make sense to take a program and start changing characters and seeing if it's going to improve the error. Like, what happens if I take a program and change a character? It's going to crash, right? It's not going to do anything, right? It just is it's really difficult in practice to search this space. Whereas deep networks, we do actually have really good methods for doing local search. So one thing, they're continuous, they're amenable to this local search. And it seems that this local search frequently succeeds. And that's maybe why, if we go back to these generic mode of computations, we talked about Turing and Shannon with the circuits, and later von Neumann with the RAM programs. Why maybe neural nets, which didn't catch on as a model of computation, did catch on for learning, right? Because really what we want to learn, we want a generic model of computation, right, that can capture anything, but that's amenable to local search, right? And neural nets are exactly a model of computation that's amenable to local search, right? That we can just change the weights a bit and things change a bit, right? Okay. And maybe this is the success. And so really what happens is that even though neural nets are provably not learnable, we have lots of empirical success. So what's going on here, right? Why are we succeeding in training neural networks? And this is, to me, the big question, right? So, and there has to be, we know that we can't learn any neural network. We have these negative results. So there must be some kind of magic property, okay, some kind of real inductive bias that tells us that, under this magic property, actually we can, if reality obeys this magic property, then we can actually train a neural networks using SGD. Now, I have no idea what this magic property is. The only thing I know what this magic property is not. This magic property is not being representable by a small neural net. That provably I know is not sufficient. It has to be something beyond that. So that means that if you go to your favorite vision researcher and ask them, okay, why is learning with neural networks good? And then tell you, because there are low-level features and mid-level features and high-level features, all this can be captured well by neural net. What they're telling you is completely irrelevant. You're just like, it doesn't tell you anything, completely the wrong answer. Why? Because all they're telling you is about expressive power. I already know that neural networks have expressive power, but I also know that just being expressible by neural network is not sufficient for being learnable, efficiently learnable. Okay? And so there is some magic property, but the magic property is completely different. It has nothing to do with it. Okay? And this is, I think, the biggest, still, and by far the biggest question about neural networks. But that's not what we're going to talk about today. What we're going to talk about in the second half of the tutorial today, we're going to try to revisit again these notions of capacity and expressive power and how they actually play out in neural networks. Okay, so we'll meet again in 11:15. Okay, thanks.
So in the interest of time, maybe we defer questions to the break session and we meet again in 11:15.